So last time we defined tangent vectors, right? Okay, so okay, M surface is a surface in R3. If we have a point in M, then we have the tangent space, and tangent space is normal to a let's say normal vector and P. So something like this, let's say. And in case your surface is obtained by an equation like this, then normal vector can be chosen as is parallel to gradient of G, right? At the point P. So that's the lemma we proved last time. As an example, for example, this be the surface given by the equation x1 squared, x2 squared, x3 squared equals 1. So just the sphere. So in this case, this surface is just G equals, so this surface is given by G equals 1, where G is this polynomial. Right? So at any point, the gradient and P is just can be chosen as the gradient of G. And what is the gradient? It is just 2x1, 2x2, 2x3 at the point P. If P is the point, let's say, with coordinates P1, P2, P3, then this is just, of course, 2P1, 2P2, and 2P3. Well, suppose we are at this point. So here is the tangent plane, okay? And this is the normal vector. Normal vector. Gradient. We can write down the equation of the tangent plane. How? Well, it passes through the point P1, P2, P3, and the normal vector is just 2P1, 2P2, 2P3. So what would be the equation? Equation is just x minus P1, x2 minus P2, x3 minus P3, dot product, the normal vector, right, is equal to 0. So yeah, P1, x1, P2, x2, P3, x3 equals actually, I can just choose normal vector half of this, right? Or yeah, I can choose half of this. If I want unit vector, then this would be just 1, right? Because I have P1 squared, P2 squared, P3 squared, which is 1. Değil mi? Bunu da çarparsanız x P1'in karesi, P2'nin karesi, P3'ün karesi olacak. O da -1. Öbür tarafa atarsanız +1. Okay, we have a definition. Let V be a vector field, tangent vector field. On M, and let F be a differentiable function. Then the derivative of F along V at the point P. Well, V is a tangent vector. Şöyle yazayım. This is the common value. Okay. How can we compute the derivative, right? On a surface. let's say we have a point and a tangent vector, and I have a function f, real valued function, then the derivative of f along the vector v just the directional derivative actually, right? This is just, so vf is just the gradient of f times the vector v, but that is also, we know that is equal to d dt of f of alpha t at t0. What is alpha t? Alpha t is any curve, so that at 0, it's at this point, and its vector, tangent vector or velocity vector is the vector v, right? So when you, if you take the derivative of this using chain rule, this is what you would get. Okay. This is actually something we already know. Okay. We start so-called chapter 5, shape operators. And the first section is the shape operator of a surface in R3. Okay, so yeah, but to define this, I will need some notation. Okay, so okay. Before we define a shape operator, we have to introduce, need to introduce use so-called covariant derivative. Okay, so let me do that. Covariant derivative is actually is a modern term. It is the basic thing in the language of differential geometry. There are some books in in undergraduate level which doesn't use covariant derivatives at all, but this is a modern book, and I think it's good to learn this at this stage. Usually covariant derivative is taught in mathematics departments as a graduate, in a graduate course, but I think this is a actually good place to learn covariant derivative. Okay, let W be a vector field on R3, and let V be a tangent vector to R3 at a point P. Okay, this is a vector field. V is a single vector at a point. Then the covariant derivative of W with respect to V is the tangent vector This is the notation, blah blah VW. Okay. Defined as follows. Inside W, you feed P plus TV, and then you take derivative of this and compute it at t equals 0. So here P is the point fixed, V is the vector, right? T, P, R3. So the only variable is t here. I am taking derivative with respect to t of this object and compute it at t equals 0. Okay. Okay. Let me draw you a picture. Suppose vector field is something like this. Okay. At all points, I have some vectors like this. Okay. And at some point, P, I am given a vector suppose this is the point P, and I am given a vector here, V. These are the vectors of W, the vector field W, okay? And I would like to take the derivative of W at this point along this vector, okay? So I wonder how W changes at this point in this direction. It is exactly this expression. Okay, I am changing. I am here. What is this? This is the instantaneous change in W at the point P, because when I plug T equals 0, I obtain the point P in the direction of the vector V, right? If I move in this direction, how this vector field changes. That's sorry. Here you see this is the derivative of the vector field along this single vector V. But later we will see that we may choose also this gadget a vector field. Okay, but to define this, I don't need a vector field here. A single vector is enough. Okay, but here I have a function of something. What is that? Function of vectors. So it's a vector field. Okay, again I am taking derivative of a function along some vector, but this function is also a field of vectors. Okay, so we are taking derivatives of vector fields along vectors. Okay, the thing is that to define this derivative, I need this gadget to be defined not only at the point P, but in a neighborhood, right? In a neighborhood containing that point. But for this, the direction along which we will take the derivative, I don't need V to be defined on a whole neighborhood. It is enough for me, that vector is defined at a single point. Okay, that's the meaning why, I don't, I take V to be a single vector at a point, but W a vector field. Değil mi? Yani bir fonksiyonun bir noktadaki türevini alacaksınız directional derivatifi. Fonksiyon tabii ki o noktayı içeren bir komşulukta tanımlı olması lazım ama vektörünüz single bir vektör olsa yeterli. Değil mi? So that's the covariant derivative. Okay. Let's do an example. So I will, continue this, but once I am done with this covariant derivative stuff. So let's look at this. So this is my vector field, let's say. X squared u1 plus yz u3. And my vector is -1, 0, 2 at the point 2, 1, 0. Okay. So to take the directional derivative of V along V, I need to compute this gadget and then take the derivative. So what is P plus TV? Well, P is this point, 2, 1, 0 plus T times V. V is this vector, right? So P plus TV is just 2 minus T, 1, and then 2T, right? This is what's happening. I am at this point, and I'll look at this line, and this is my vector V. As T changes, I am just moving on this line. All right. Now, covariant derivative is just W composed with this. So let's see. What is W? P plus TV. Well, this is just W of 1 and 2T. All right. And what is this expression? So if I plug X, Y, Z, this is what I get. So X is just T minus, so 2 minus T squared U1 plus Y times Z. Y times Z is just 2T U3. Okay. So what is this covariant derivative? It is just d dt of W P plus TV at the point 0. You see, when you plug T equals 0, you are really at this point P, right? So it is not just an arbitrary curve, but it's a curve that passes through the point P at T0, and it has velocity vector V at the point P. All right, so I need to take derivative of this gadget. What is the derivative of this? It is 2 times, well, minus U1 plus derivative of this. It is just 2 U3. And you need to compute this at T equals 0. When you plug T equals 0, you get minus 4 U1 plus 2 U3. Okay. Anlaşıldı mı? Let me erase the board. Okay. Another example, let's say, what would be this derivative of the constant vector field along a vector? What would be this? Right? This is a derivative, right? It measures how this gadget changes at a point along this vector. But if this is a constant vector field, U1 is this vector field, right? At any point, this is just 1, 0, 0. So what is the derivative of this? Just 0, right? There's no change. So this is 0. Since U1 is a constant vector field. Okay. Here, of course, W is not a constant vector field. It changes from point to point. All right. Here is a lemma. If W, let's say Wi, Ui is a vector field on R3 and V is a tangent vector. Okay, let me just write it this way. V is a tangent vector to R3 at the point P. Then the covariant derivative of W of this vector field along this vector will be just I from 1 to 3, V of Wi, UIP. Now let's see the proof of this. Here, of course, W is this. Here, of course, W are just functions, right? Real valued functions. These are the coefficient functions, like this one. Right? So this is W1, this is W3. W2 is 0 because the coefficient of U2 is 0. Yeah, here in this example, W1 is this function, which is x squared. W3 is this function, y times z. W2 is 0. Okay. Well, let's look at this gadget. So what is this? This is just d dt of what? W t plus tv, right? At t equals 0. But what is w? W is this expression. So it is just this wi, right? I put this gadget inside this function, right? Ui is my unit vector, right? I take the derivative of this at t equals 0. Well, what is the derivative of this? This is just summation from 1 to 3 and derivative of wi t plus p plus tv, right, at t equals 0 times ui, right? Ui is the constant vector, 0, I mean, it is 0 everywhere, 1 at the ith coordinate. And what is this gadget? This is the directional derivative of the function wi at the point P along the vector V. Well, this is just, if you want the gradient of this function, dot product V, or what is this? This is just V of W. I should say, right? So what we get is just I from 1 to 3, V W I U I. Okay. So this finishes the proof. Ya da şöyle yapayım. Şu silene kadar. Okay, we have a theorem which describes basic properties of covariant derivative. So let B and W be tangent vectors. Vectors to R3 at a point. Y and Z be vector fields. On R3. Then for real numbers A and B and functions, real valued functions F and G, we have okay. The first statement is just if you take linear combination of these two vectors V and W, okay, I just multiply them by some constants and add them up. I get another tangent vector. And the covariant derivative of y along this vector is just what? This is a times covariant derivative of y along the vector v, and then b times this. Yes. So if these are just some real numbers, it splits like this, so it is kind of linear in the vector component. And here also I can take the scalars out because these are scalars, so they just go out like this. However, if you have a function and you multiply your vector field with that function, then you have to be careful because this is not a constant, so you cannot just take it out. You have to apply Leibniz rule, right? This is just a derivative. So you have to take the derivative of this times this plus this guy times derivative of this. So it will be what? Derivative of this along the vector v, so it is just v of f times y plus f times derivative of y along the vector v. That's the covariant derivative. Okay. This is just the Leibniz rule. Derivative of f along v is this object. Derivative of y along v is this object. Okay. They are both derivatives, but they have different names. One of them is called covariant derivative. The other one is called just directional derivative. And the final property is that v of y dot product z. These are two vector fields. I can take their dot products, and dot product is a real number at any point. So this is a real valued function, and I just take directional derivative of that function. So derivative of a function will be, of course, another function, and here it is. It is derivative of this guy, which is just this, and then I have dot product, so I multiply with this, plus y dot product derivative of z. Okay. Well, proof is easy. Let me do some of them. Okay, let me do the first one. Okay, so what is this? A V plus. This is just derivative of what? Is in y, I put here what? The point P plus T times AV plus BW, right? I take derivative at the point 0. Okay. And what is this gadget? Well, derivative of this gadget with respect to t. I take derivative of y with respect to this gadget. So that will be just bir dakika. Pardon. Yeah, I have to do the following. So y is a vector field, right? It has components, let's say y1p, y2p, y3p, right? A vector field. Here, each yi is a function from R3 to R. So I take derivative of this expression y1 p plus t times AV plus BW. Okay. Y2 times Y2 of P plus T AV plus BW, and Y3 P plus T AV plus BW, and I take the it's 0. Now let's look at the first term here. This is just a function. I am taking its derivative with respect to t. What is this? This is nothing but the directional derivative of this function at the point P along this vector. So this is just directional derivative. Therefore, this is just, gradient of this function at the point P, dot product with the vector AV plus BW. Plus the same thing for the whole other terms. Neyse yazayım. Y2P dot product AV plus BW plus right. I shouldn't have plus, I should have commas, right? Yes. Here I have commas, so. All right. So let me switch the board. So the the covariant derivative along the vector AVBW of y is then what? This expression. And what is this gadget? What is this gadget? Well, this is just, right? This is the dot product of two vectors, and this can be written like this: A times A y1 P dot V plus B times y1 P dot W, right? So, yeah, let me write that one. A times y1 P dot B plus B times y1 P dot W, and the same thing for the other two vectors. But what is this? This is just A1 and then okay, so yeah, şöyle yazayım. Okay, I can write this as follows: A times del y1 P at V del y2 P at times V. Yes, and then
Hocam tahta kaldı mı?
kaldı mı? Özür dilerim. So okay, directional derivative of y along this vector is equal to this expression. Here I have comma, and then the same thing with y2, and then with y3 for y3. This gadget breaks into two parts. I take this part, the first part of this summation, and then the first part of the second term, and the first part of the third term. So I will have this plus B times del y1 P dot W y2 p dot w, y3 p dot w. But what is this? Is here, right here, this was just, you know, the directional derivative of this expression, and that was this derivative, and that was by definition this expression. So I have almost the same thing there. So what is this? You know, if I just go backward, this is just a times the covariant derivative of v of the vector field y, whose components are y1, y2, and y3, plus b times the directional derivative along the vector w of, again, y. Okay. So I'm just going these steps backwards, okay, and obtain this gadget. Okay, let's give a break. After the break, I'll continue.